The concept highlighted in this module deals with the problem of finding an optimal order quantity in the face of uncertain demand. The story that motivates our analysis was originally referred to as the Newsboy problem. More modern text will call this the news vendor problem, but the story is the same. The news vendor goes out each morning and buys newspapers from a visiting truck that has a fixed route. This means that the vendor places an order before demand is realized. When the story was originally formulated, the news vendor paid a simple fee per unit ordered, and there was no recycling of newspapers. Therefore, inventory only had value for a single period. If it turned out that the order size was less than demand, the news vendor had a lost sale, and there was no way to get it back. If it turned out that the order size was greater than demand, the news vendor had leftover newspapers that could not be sold. We need to find an optimal order size for this setting. Let's refer to our order size as Q. Consider what happens when we increase Q by 1 unit. There are two major factors that have to be balanced. There is some benefit of increasing the order size. This must be true because there's a benefit of selling one more unit. This is simply the revenue per unit sold minus the procurement cost. On the other hand, the vendor incurs a cost if he cannot sell the unit. This is the money spent to procure the item. If we could sell leftovers for some fee, we would call this the salvage value, but for now, let's assume that this value is 0, so the marginal cost is simply the price the unit paid to his supplier. This is the problem that we look to solve. The underlying trade-off should be pretty clear. When we increase the order size, the probability that we run out of papers before all demand is served must drop. On the other hand, the probability that we have at least one paper left over after all customers are served must rise. So we can say that the optimal order size must be where the expected marginal cost of ordering that last unit is about equal to the expected marginal value of ordering that same unit. We emphasize that this is the expected marginal benefit because what we really mean is the marginal benefit if the unit can be sold times the probability that it can be sold. The expected marginal cost refers to the cost if a unit cannot be sold times the probability that it cannot be sold. If we order a pile of Q newspapers, we can say that unit Q is the newspaper on the bottom of the pile. We have to ask whether demand will be greater than Q or less than Q. If demand is greater than Q, then we can sell this last unit, but this probability drops as Q rises. If demand is less than Q, then we cannot sell this last. If demand is less than Q, we cannot sell this last unit, and this probability rises as Q rises. We seek the level that finds a balance between these two factors. The probability that demand is less than Q is the same as the CDF of demand evaluated at Q. Let's call this value P. So the probability that demand is below Q is now written as P. This means that the probability that demand is greater than Q is simply 1 minus P. We are looking for the smallest value of P, where expected marginal cost exceeds expected marginal value. So P must satisfy this equation. If we just rearrange terms, we eventually get to this simple result. The best order size is the one that corresponds to a specific p-value, which in turn corresponds to the point on the CDF of the demand distribution that balances marginal benefit and marginal cost. This means we solve the problem using a two-stage process. First, we calculate this critical ratio that I write here as marginal benefit over marginal benefit plus marginal cost. We then look at our demand distribution and find the number that corresponds to this value. Before we close, we need to emphasize 3 important facts. First, we assumed that the benefit from an extra sale is linear. In other words, we assume that the per unit procurement cost and per unit sales price are both fixed. Second, we assume that the cost of having leftover units is also linear. In other words, we assume that the per unit procurement cost and per unit salvage value are both fixed. Third, and most importantly, we assume that we have some CDF of demand that we are willing to work with. Note, this does not mean that I have a good estimate of demand. If my best guess is that demand is anywhere between 1 and a million, this simply means the best CDF of demand that I have is uniformly distributed between 1 and a million. Even if our guess about demand is really bad, the logic guiding our decision doesn't change. We have only made the very weak assumption that some CDF of demand exists.